Okay, so after we prove the residue theorem, it is very clear the importance of the residue, right? So we need to figure out what is the residue for a function with a isolated pole. Isolated singularity. Now let's see one case. Isolated singularity, if it's removable, you consider it's not a singularity. If it's a pole or essential singularity, we will have a different method to prove it, to find the singularity. So let's see here. Suppose F has a pole of order m. M is greater than or equal to 1 at z equal to a. Okay, if we have such singularity, it means this function z minus a to m's power times f of z has a removable singularity, right? Removable singularity, let's just ignore it because removable just means it's removed, right? So g of z has a power series representation. It's like the b0 z minus a, sorry, not b0, bn z minus a to n's power n's from 0 to infinity. And then from here, we have f of z is equal to what? F of z is equal to b0 z minus a to m's power b1 z minus a to m minus 1 until what? Until bm minus 1 z minus a to power 1, and then plus here it becomes the power series start from 0 to infinity. All right. Okay, so this is also the Laurent expansion. So here the residue of f of z is this bm minus 1, bm minus 1, the residue. So it is a residue of f with respect to a. Now what is a bm minus 1? If we want to compute bm minus 1, you're going to check that bm minus 1 is the m minus 1's derivative of g evaluated at a and divided by m minus 1 factorial, right? So this is the situation. So we have our formula, proposition 2.4. 2.4 says, suppose f has a pole of order m at z equal to a, and let g of z be z minus a to m's power times f of z. Then what is the residue? The residue of f with respect to a is equal to the bm minus 1 is equal to this. This is 1 over m minus 1 factorial g m minus 1. The m minus 1's derivative of g evaluated at a. Right? So that's the proposition. The proof. This is a proof. We actually find the formula first before we state the theorem. And this, while this is not an easy job to find the m minus 1's derivative, but at least we do have a formula. A little remark is that if m is equal to 1, then f of z becomes b1 z minus a and plus sigma from 0 to infinity, the rest of the part. And we're looking for this this quantity, the first leading coefficient. So b1 is actually the limit z approaches a, z minus a times f of z, right? You see, you multiply z minus a times with f of z, you will get b1 plus the sigma is start from 1 to infinity. From 1 to infinity, they all contain the coefficient z minus, the factor z minus a. So when you let z approach a, it becomes, this tail becomes 0, so you only have b1. So this is the residue of f with respect to a. So when the pole has order m, has order 1, the residue is easy to compute. All right, so the residue becomes easier. This is a residue of the pole of order 1, Okay, now let's try to apply the residue theorem to certain computation. This is one of important application in the real integration, improper integral. So we're going to show that the integral from negative infinity to positive infinity, x squared over 1 plus x to the 4th power dx is equal to pi over square root of 2. All right, so it looks very difficult because we don't have such computation before, and the denominator cannot be factored. It has no real zeros. You cannot apply the partial fraction method. Okay, now let's see how do we prove it and how do we apply the residue theorem. So we're going to apply a complex analysis. We're going to define the analytic function, or possibly with pole, with a singularity. So we define f of z to be z squared over 1 plus z to 4th power. Then f has 4 simple poles. Simple poles means the order is 1. All right, so those are the z equal to -1 to power 1 over 4, right? So -1 we write like e pi I, take power 1 over 4, so you will get e to pi over 4 times I, and then e to plus 2 pi I, so it's a 3 pi I, okay? So pi I, so this is a process. It is e pi I plus 2 pi I. You do not change it. E to 2 pi I is 1. So this is a 3 pi I, so e to 3 pi over 4 and I. And z here plus 4 pi I is a 5, so it's e to 5 pi over 4 times I. And the last one, and plus this is a 2, here's plus 4, and then plus 6 pi I. Your plus 6 pi is a 7 pi over 4 times I. You cannot plus 8 pi. You plus 8 pi, you come back to the e to pi over 4 times I. All right, so there are four simple poles. 4 simple poles. Okay, so where are those 4 simple poles? So you have complex plane, pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. E. those pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4 are the argument. And they all have the property that the fourth power is equal to -1, right? All right, so let's compute the residue. Let's compute the residue. For example, if we have the residue of f z1, let's put z1. z1. It is by definition the limit z approaches z1. Let's call this is z1. This one is a z2. This one is a z3, and this one is z4. Z minus z1, z squared over 1 plus z2 fourth power. Okay, so this is actually what? This is actually, if we imagine it, it's a z minus z1, z squared. The denominator is actually z minus z1, z minus z2. Remember the fundamental theorem of algebra. Z minus z3 and z minus z4. Okay, so you actually cancel z minus z1 with z minus z1, and you will have z squared over z minus z2, z minus z3, z minus z4. And this function is well defined at z1, so you're going to put z1, evaluate at z1. So it's a z1 minus z2, z1 minus z3, z1 minus z4. All right, so this is a z1, z2, z3, z4. Okay, now let's compute z1 squared. z1 squared e to power pi over 4 times I squared is e pi over 2 I is I, right? You just get to this point. The argument is pi over 2 is a vertical. The radius is 1, so it's I. The numerator is I. And z1 minus z2 e pi over 4i minus e 3 pi over 4i. Well, let's compute. This one is cosine pi over 4 plus I sine pi over 4 minus cosine 3 pi over 4 plus I sine 3 pi over 4. This one is negative. It's negative square root of 2 over 2. Right? And this one is positive square root of 2 over 2. This is a square root of 2 over 2 plus I square root of 2 over 2. You do subtraction. So you only have square root of 2 plus square root of 2 over 2. So it's a square root of 2. So z1 minus z2 is a root 2. z1 minus z2 is root 2. And let's try to do them one by one. I'm trying to really examine this answer. z1 minus z3 e pi over 4i e 5 pi over 4i. So cosine pi over 4 plus I sine pi over 4 minus cosine 5 pi over 4 plus I sine 5 pi over 4. Okay, so this is a root 2 over 2 plus I root 2 over 2 minus cosine 5 pi over 4. Cosine is also negative root 2 over 2. And this is negative I root 2 over 2. So it's a root 2 plus I root 2. So you double root 2. Actually, it's the same. It's exactly you double this. And z1 minus z4, it's a e pi over 4i minus e 7 pi over 4i. Okay, there's no easy way to do them. Just be patient. So cosine pi over 4 plus I sine pi over 4 minus cosine 7 pi over 4 plus I sine 7 pi over 4 over 4. So it's a root 2 over 2 plus I root 2 over 2 minus this part. 7 pi over 4 is here. So it's a root 2 over 2 quadrant 4. So minus I root 2 over 2. So it's a I times root 2. Okay, so this is the third factor. So let's evaluate. So we're going to put it here. The numerator is what? The numerator is where's the numerator? I did the numerator here. The numerator is I. So it's equal to I over what? I over first one root 2 and second one root 2 plus I root 2. Third one I root 2. Oh, cancel I. And root 2 times root 2 is 2. So it's 2 times root 2 plus I root 2. Right? And let's multiply. This is okay. 2 root 2, 1 plus I. Let's multiply top and bottom 1 minus I. Right, okay? So it's a 1 minus I. Here, this is a 1 square plus 1 square minus I square. I square is negative 1. 1 minus negative 1 is plus 1, so it's 2. 2 times it is 4 root 2. Okay, so it's a 1 minus I over 4 times root 2. So that's how they get this quantity. Okay, so in the textbook, they directly put this answer, but you really have to do all these computations. There's no quick way to evaluate. Okay, good. So we just exam one. This quantity. Similarly, I will really just say similarly. But if you do it in the qualifying exam, you really have to compute because you never see the answers. Here we just copy it. Similarly, the residue of f with respect to z2, which one is z2? Here, this one, is equal to negative 1 minus I 4 times square root of 2. So we just compute the residue of f with respect to z1 and with respect to z1 and z2. Okay, we only compute these two. You can compute the other one, but because later we don't use the other two, so we will not compute them. All right, excellent. So we have two residues. Now we're going to construct the homologous to zero path. This is a semicircle. So let capital R be greater than 1. It's radius. And let gamma be the closed path, which is the boundary of the upper half of the disk of radius r with center origin, with center 0. Okay, so this is the path gamma. And what is the orientation? Traversed in the counterclockwise orientation, direction. All right, so you go this way and you go back. And r is greater than 1. R is greater than 1. So here is a z1. Here is z2. they are included in this upper half disk. All right, so what we know by residue theorem. Residue theorem says 1 over 2 pi I integral f along gamma is equal to the winding number times the residue plus the winding number times the residue. Okay, so the winding, this is a very simple curve. The winding number with respect to whatever point inside is always 1. So it's a 1 times the residue plus 1 times the residue. Okay, so that's why we get residue plus residue. Actually, they are both multiplied by 1. Okay, so that's why we only compute those 2 residues. The other 2, they are very interesting, but they are not used in this problem. Okay, so let's add them. So here, this is 1 minus I over 4 root 2 plus negative 1 minus I over 4 root 2. We did this computation. We didn't do this. And you see here they have the same denominator, so you add the numerator, cancel 1 and negative 1, so you get a negative 2i, negative I over 2 times root 2. 2i cancel the 1 copy of 2 from the denominator. Clear? So this integral is equal to this, negative I over 2 times root 2. Very good. Well, that's one part. Let's leave it here. Let's leave this part here. On the other hand, this integral, well, you have 2 pieces. We're going to write them in 2 pieces. Integral from negative r to positive r. In this moment, when z is along the x-axis, so z is just x, so it's what? It's x squared over 1 plus x to 4th power dx. dz is just the dx. And the other part, when it is along this curve, this is z is equal to REIT, right? REIT. So dz is REI dt. You differentiate with respect to t. And z squared is r squared E2IT. Okay, so the numerator, and tt is from 0 to pi, not 2 pi, it's just upper. So the numerator is z squared times dz, so it's r cubed E3IT and times is I and dt. This is numerator. And denominator is 1 plus r to 4. Z to 4th power is r to 4 E4IT. E4IT. Okay. All right, so this I and this I, these 2 I are canceled. So that's why in the textbook you don't see these 2 I's. They are directly canceled. Okay, so what we have? We have, of course, we will cancel this 2 pi I. If we cancel 2 pi I, we'll have this part. This part is this. Negative I over 2 times root 2. So we're going to multiply this equation by 2 pi I. 2 pi I. So it's this quantity times 2 pi I. Minus this quantity. You are going to move this quantity to the left side. To the left side is subtraction. And it has a 1 over 2 pi, no I. E3IT r cubed 1 plus r to 4 E4IT dt, and then times 2 pi I. Okay, I just want to make sure I don't have the wrong computation. Okay, 2 pi cancel, you have I. And this I times negative I is a 1, so you don't have it. 2 and 2 cancel, so it's a pi over root 2. Okay, so that's why how you get a pi over root 2. Minus r cubed times I, r cubed times I, integral from 0 to pi e3it 1 plus r cubed e4it dt. Okay, so that's how we cancel as much as possible and have the following stuff. Okay, so remember we assume this integral exists. This integral exists. Okay, so we're going to let r approach infinity. Let r approach infinity. If r approach infinity, this left side, right side, left side is just the integral in the problem. The left side becomes integral in the problem. We are trying to compute the right side. This is a pi over root 2. It's a constant. It does not change. So we're going to compute what this is. Okay, let's continue. 1 plus r to 4 e4it. Remember, we have triangle inequality. It's greater than or equal to r to 4 minus 1. If it becomes a subtraction, it's greater than. If it becomes addition, it's less than. Right? So 1 over 1 plus r to 4 e4it modulus is going to be less than or equal to r to 4 minus 1 for all t. Okay, now let's try to study this ops value. Ops value r cubed I integral 0 pi e3it 1 plus r to 4 e4it dt. We're going to estimate it. So I has modulus 1, so ignore it. And you are going to put this ops value into the integral. e to 3it has modulus of 1, so you don't have it. Okay, so we directly have this less than or equal to. And this one is less than or equal to 1 over r to 4 minus 1. 1 over r to 4 minus 1. So we have r cubed r to 4 minus 1. And then this is integral 0 to pi dt. That's pi, right? So this is a pi r cubed over r to 4 minus 1. And this quantity converges to 0 as r approaches infinity. Right? This converges to 0 as r approaches infinity. So after we apply the limit of r approaching infinity, we have integral from negative infinity to positive infinity, x squared over x to 4th power, 1 plus x to 4th power dx is equal to this pi over square root of 2 minus 0. And we are done about the computation. All right, so in this problem, what did we do? We construct a proper curve. We make sure that this curve encloses enclose some singularity, and we can compute the residue of the singularity. I don't say we always compute the residue of singularity. Some functions, if it's too complex, there's no uniform way to compute it. All right, so we can compute the residue, and then we will modify our curve. When r becomes bigger and bigger, we modify our curve, and we will get the useful element. Non-useful element we have to manage to let them vanish. This is vanish. When r approaches infinity, it disappears. This term will disappear when r approaches infinity, so you don't worry about it. You only choose the useful material. Right? So this class of examples is a very, very creative and tricky. So you must do sufficiently many exercises in order to handle this residue method to evaluate certain improper integrals. Okay, so we will have more examples in this section, and we will continue in the next discussion. Okay, thank you very much.